Hello, it's January 2017, and this is Unseen Podcast, episode number 65. This is your host, Paul Carr, and joining me on this episode are David Grigg.
Hi.
Marcia Barnhart.
Hello, and welcome from beautiful northern Michigan.
Sam Lichtenstein.
Hello from New York City.
Yeah, I can hear the background ambulance there. And
Yep.
Nick Nielsen.
Hi from snow-covered Portland.
So this is episode 65. We had a very active pre-show discussion thread, and the four people here tonight, besides myself, are four of the five who really engaged with that. And so the discussion, what we thought we'd like to talk about tonight is the general topic of megastructures, perhaps a bit from a level of abstraction above how you build a megastructure, or how you and what a megastructure does technically, but more to why would you build a megastructure, what sort of use would you put to it, how does a civilization even get to the point where it wants to build a megastructure? So who wants to kick it off?
I would ask Paul to kick it off, actually, because I think I had originally raised the discussion topic before I'd even noticed that Paul had topic in early December. I think in the context of Tabby's star. Maybe he wants to say a few words about observational signatures that are interesting. If not, we can move on to other topics. But
I'll refer you in the show notes to my little undergraduate essay about megastructures. But essentially, I was inspired by the Benfords, two brothers and a son. I know Gregory and James. I can't remember the son's name, which I should remember because he works where I do. But anyway, they were talking about the reasons why a civilization might want to build a radio beacon that could be detected over a wide portion of the sky. And when I thought about that, I said, well, why would anybody build a megastructure? And then, of course, there was discussion in Jason Wright's and et al. Papers about megastructures and how they might be used for various purposes. So I tried to make a list of things that I could think of. And I listed, well, essentially 6 things, one of which I think is kind of minor, but of those things, one of the categories was things that humans wouldn't think of. so
that's sort of a catch-all, really, right?
Yeah, well, as a cover your ass category, I didn't think of it, but that's because nobody would. But I keep thinking, Daniela DePaulis, who was on the discussion thread, raised the notion of a religious monument or a religious act of devotion into megastructure, which actually, historically, from us human perspectives, makes a lot of sense. Because if you look at the pyramids of Egypt, you look at the big pyramids in Central America, you look at lots of other big structures, the cathedrals in Europe, they were not erected for a practical purpose at all. They were erected for religious reasons. They were an act of devotion.
But if temporarily, just for the moment, we were to stick with the kind of traditional sci-fi megastructures, do you want to just quickly run through your 5 categories?
Yeah, well, one that I think is makes a lot of sense, and that I hope that we will be doing someday. By we, I mean my great-grandchildren. Is an astronomical facility. That is
an observatory, basically.
An observatory. These days we're talking about maybe someday putting a big telescope on the moon, on the lunar far side. That's nothing compared to what you could do if you could put one in orbit around the sun. You could build a telescope that could keep track of what's going on in quite at some distance around you at different stars. You could see all the images of planets and so on. This is many generations away from what we can do now, but it certainly an inspiring thought that they might be interested in the universe around them. They might be wanting to look at really close at neighboring galaxies, and just because out of curiosity. The other one is that you might build the megastructure as a sort of monument to your civilization. We've talked about monument probes before, or monument structures. Something that is sort of a secular monument, says we were here, we were awesome, we kicked ass and we left. That was something that Benford's came up with, sort of like Ozymandias.
Can we call this the Kilroy was here theory?
Yeah, something
Yes,
like that.
I like that.
Now, I didn't in my little essay, I didn't enumerate the religious motivation, which I think Danielle may have a lead on something there. But the third one was for energy, which is the classic one, which is the Dysonian idea of capturing a lot of energy from a star. And there's different ways to do that. The classic way is just to get in the way of the starlight and turn it into some kind of form of energy that you can use for whatever purpose you have. The way we do it these days, which is certainly not at a mega level, we put solar panels in front of the star, and they capture light, turn it into electricity. Who knows if that's the best way to do it, but it worked for us. We figured out how to do it. The other way is you could actually build a concentrator. You could build a mirror that would reflect the light somewhere else. It wouldn't have to be even in that same solar system. It could be very distant. And you could use it.
Sam, they're coming to get you.
I got the windows closed. What can I say? It's New York.
Yeah,
I live near a hospital.
Might want to mute when someone else is talking.
No, that's all
I'll
right.
do that.
That's all right. It gives a little atmosphere to the thing. But the other one was and that mirror could be used to propel a big light sail, or it could be used for lots of reasons. And then I think the other one, the category that I raised was to actually move the star. You could propel the star to a new location. This is called a Shkadov thruster. This was not my idea. People have been kicking this idea around for a while. You could actually cause this by redirecting a significant portion of starlight in some direction. You could actually make the star move. And
It begs the question, Paul, of why you would want to move your star.
Yeah.
well,
That's just
maybe there's a nearby
stupid.
supernova that you're predicting.
Yeah, maybe, but you can't land the damn thing anyway.
You could never move it far enough to survive. That's just goofy. Who
Well,
came up with that idea?
maybe a guy named
Inverse
Shkadov.
square law in terms of the efficiency with which you can harvest solar energy, right? And so
Well, it turns out the
one can
Illuminati.
imagine planning generations, centuries, millennia ahead of time, and you'll want the energy located in a place where it's more efficient to collect in the future.
Millions of years in advance, you would perhaps see a young star forming near you. You say in 50 million years that thing's going to go supernova. Let's get the hell out of here. And
Well, that's the classic.
That's an absurd line of thought. That's just absurd.
why is it
that's the
absurd?
classic-
You'd be a
that's the
completely
classic link.
different being in however much time.
Well, yeah, it's not. I'm not talking about humans
Somebody
here.
was smoking a lot of dope coming up with that one.
I don't know about that. Maybe drinking a lot of vodka.
Yeah, that's a dope smoking thing.
But no,
I think.
you
I think
actually
even,
the physics works out. You
even a
can move
Dyson
the star.
swarm is a pretty far out concept, right? I mean, harvesting energy on a solar system scale is pretty far fetched.
That's far enough
compared
fetched to move the actual star is just goofy. But
Well, the question is whether you would ever think it's a profitable thing to do, right? It must require so much energy to move it that
Well, the energy
you'd
comes
have
from
to
the
have
star
a really good
itself.
justification.
The energy comes from the star itself. You just have to have a.
Yeah, but you're expending some huge fraction of it for the locomotion, right? And so you have to there's some sort of, it's like a business, right? You have to decide whether the investment of moving the star is worth.
But now that isn't even a megastructure. That's just a pie in the sky idea.
No, it'd be a megastructure. It would, actually,
it'd still be a star.
No, Marcia, the physics of it completely works out. There's nothing about it that violates the laws of nature. You can move the star.
I'm sure you can, but it's just a goofy
It takes
thing
it takes a long time, but
Just because you can doesn't mean you should.
Yeah, I mean, dude, your star was born there. Let it live and die there.
But because you can, that means you have to think about it.
It's interesting to think about it in comparison to, historical. It's not quite right to call them megastructures, but like a favorite example is the Temple of Luxor in ancient Egypt.
Yeah.
It was
moved.
Constructing it was a very many generation long project that required formulating an entire society around the idea that this was a worthwhile endeavor. Everything from religion to culture to the economy was built around this temple complex that coordinated massive amounts of labor in a way that was precedented, but relatively unprecedented for the time. You have to sort of imagine whether a civilization could get to the point where they would want to commit themselves to a project of that magnitude, It's hard to imagine the circumstances in which you would do that, but you can't say it's inconceivable that you would completely redefine your civilization around such a grand scheme,
I'm not, it's okay. It's conceivable. It's just goofy, but that's just me.
Well, if a civilization gets large enough and it just expands of its natural tendency to expand, and it becomes a spacefaring civilization that has the access to energy and material resources of a planetary system, and you have automated manufacturing systems, there's no reason that you can't send out your automated nanobots to start constructing very large projects, behind your back, as it were, without much initial investment. I mean, once you have that suite of technology, obviously we don't have that suite of technologies yet, but once you have automated manufacturing in space, so it has access to energy and materials, it should be able to, in principle, manufacture structures of arbitrarily large size.
Right. You wouldn't move your star. You would move your populace around the star to gain its best advantage. And that way you'd build a large megastructure that you lived on and died on and continued to construct as you were living and dying on this structure. And it would
move about a star system. Maybe artificial intelligence, Marcia 2.0, decides that that's not how the calculus works out, I mean, I feel like we're falling very naturally into the question Daniela raised in the pre-show discussion about whether civilization naturally draws people towards the concept of megastructures, grand scale, larger and larger expenditures of energy, whether it's inevitable or whether it's kind of a cultural bias that we have in our way of conceptualizing the future.
Well, I think it can be both, although that sounds contradictory. But yeah, Daniela DePaul has made some really great points on the thread, and I wish that she could join us to talk about them, because there is a lot of weirdness in terms of our cultural legacy and even the Stalinist gigantism in some of these ideas. But it's not only that, because like I was saying earlier, if civilization continues to grow of its own inertia or momentum, as it were, just to do things, just to be able to continue that growth, if you want to continue to do science, your science projects have to get larger and larger. Like Paul was talking earlier about, astronomical observatories. It's not just that, but building a particle accelerator that has a ring, say, as big as the orbit of the Earth or something like that. You could do much more high energy physics if you want to keep making discoveries, whether it's astronomical discoveries with a huge telescope, And I posted an older paper by Kardashev and several others on the Unseen podcast page about an indefinitely expandable space radio telescope, which is a great example of the kind of project that could be built in space and just keep getting bigger and bigger and bigger over time. And as it got bigger, it became more sensitive. So that's a kind of scientific instrument that could be built in orbit. And the motivation for it would be, if you have a scientific civilization that's seeking more scientific knowledge, if you want to keep making discoveries, you have to make larger instruments.
Yeah, we're already getting very good at phased arrays in the radio frequencies, which, for example, the Allen Telescope Array in California, which is used for SETI, it's really not a big conceptual leap from that to an enormous one in orbit somewhere that would have a gigantic aperture.
The question I would have is would that sort of thing be, in terms of a megastructure, would it be something that we could see from Earth if it was around a star 500 light years away, for example? To me, a megastructure, and the whole interest in megastructure with Tabby's star and so on, is there something that an alien civilization would build around a star that we could detect from here and know unambiguously that it was, in fact, an alien civilization that had built it? Now, apart from an actual Dyson sphere or something occluding the star to a huge extent, I don't think any of these things we've discussed so far would be actually would fit into the category of a megastar, of a megastructure.
I would think
from that far away.
The engine Paul was discussing about moving the star itself would definitely have a thermodynamic signature that would be detectable depending on your angle with respect to the star.
It would depend on the efficiency of the mirrors and how close they were to the star. It might be hard to see. Unless the star is moving right away from you, in which case you'd see the tremendous concentration of starlight. And you'd see a star that was much brighter than it should be for its distance, which, we're getting much better at measuring distance to stars these days. So there's hope we can see that. The other thing is that any sufficiently large structure, if it happens to transit its star relative to us, should have a transit signature. Now, I've arbitrarily defined a megastructure in my blog as something as large as a planet. Now, how big is that? Planets vary over the size. I would say something on the order of a few thousand kilometers and up. And so whatever transited Tabby's star, as seen by Kepler, was on the order of 100,000 kilometers or more. It was really big. We don't know. We don't know that it was artificial. There's no clear. We don't even know how to ask the question: was it artificial? Because
didn't they just come out with some evidence that it looks like it was a planet that got gobbled up by that star?
No, they didn't. The press is completely played
that. Was not accurate at all?
No, well, the paper was fine. But the paper only attempts to explain the long-term dimming and not the dips in the Kepler light curve. But of course, the mainstream media will get a hold of it and completely distort it and get it wrong.
But debris would account for the dips.
Not very well, not very easily. It's a stretch.
So the mystery continues.
Yeah.
But the long-term dimming is kind of, I felt, was a deeper mystery than the dips. Well, maybe that's an incorrect perception, but the dips, you can imagine, were an instrumental artifact, whereas the long-term dimming was kind of an independent source.
The dips are clearly not an instrumental artifact. No, they're not. There is some discussion about how much the dips might be related to the existence of another source nearby, but it's not. They don't go away when you add that in. They just get a little different, and that's controversial. So now, is there some clever astrophysics that might explain the dips and the long-term dimming? Nobody knows. It hasn't been developed yet. So it's entirely possible. But the question with this the megastructure, the reason I wrote the blog entry is nobody's. Well, I should say nobody. There's not enough work done on what we expect to see from a megastructure. And so you're talking about observables, David. That's exactly what we're trying to get to is, why would, and all we can do is think as human beings. We can't think like aliens. I say, why would we build a structure that big? And if we did, big enough to create the dips in Tabby Star, something bigger than Jupiter. Jupiter would not create the dips that size. Tabby Star is a big star.
Okay, here's what's happening. It's getting dimmer because they built this machine to move their star farther away. The very thing you were talking about.
Well, that wouldn't cause that.
What if it's accelerating away and it's dimming because it's farther, and these little structures that are making it move are the things that are occluding the light occasionally.
Well, the structures
My
could.
God, they did it.
The structures could transit, in which case that would explain. That would explain it, but we're not seeing the way the Tabby Star is moving, and the distance is completely normal and unsurprising.
We see a redshift anyway. If it was moving away, we'd see a redshift.
Oh yeah, we see a very ordinary radial velocity.
The point, I guess,
you might also imagine you'd see a reason why they might want to move their star if in fact they were trying to move their star.
Good point, and we don't see that in the case of Tabby Star.
The point I was trying to get to about being able to see these things, if there's a structure as big as you're saying, way bigger than the planet Jupiter, why would any civilization build a solid structure that big? I mean, with a Dyson sphere, no one ever thinks that you would physically encase the star in a rigid structure. That's kind of crazy.
Well, it doesn't need to be a rigid structure at all.
No, but that's my point. The idea really that Dyson had was that you'd have perhaps lots of little asteroidy things that were all swarming around the star, collecting its energy and so on. But that idea wouldn't explain what we see at Tabby Star, because what we see apparently at Tabby Star is something
true?
Solid and big.
Well, we don't know that it's solid. We just know that it's large.
Right, like the observational signature points to the size of the disk that you see, occluding the starlight, right? It doesn't.
Yeah.
It doesn't say anything about what the mass of that occluding object might be, right?
No.
It could be anything between a swarm of small things or one giant massive thing.
Would we see the difference between a swarm and a solid thing? It seems to me that a swarm would be almost as hard to use as an explanation as the idea of clouds of comets and so on, or debris from a.
Well, we don't know how the swarm would be engineered. It could. There's problems with the building a swarm, and the problems are not unsolvable, but they're difficult. The second set of dips in Tabby Star are very complex, which suggests many components to the whatever it is that's transiting. And the first dip is the weirdest one. It's a very simple, sharp dip down to a minimum, then right back up over just a few days. And it sure as hell looks like a solid thing transiting, but it doesn't have to be. It could be many things transiting in a tight formation. But the second set of dips don't look like that at all. So right now there's a very poor understanding of what that would be, and that's why I donated to a Kickstarter to monitor the star so we can find out when it dips again, and then get all the world's best observatories looking at it in lots of different wavelengths. And that I think that'll happen if we find it again.
And just to get the cards on the table, it's my impression that there's engineering reasons why non-swarm types of megastructures are more far-fetched. For example, a solid ring world a la Niven, or a Dyson shell type structure are actually pretty far-fetched from an engineering standpoint.
They are. They require unobtainium.
The stresses that the materials would have to withstand are actually not really plausible physically.
But with many megastructures, they're they are modular and join or disjoin when you want them to.
Wait. You know something about megastructure? Because the rest of us are completely in the dark.
Oh, piffle.
No, I think Marcia's right. The swarm type, the more modular type designs sort of seem more accessible from our current understanding of engineering. That seems like a fair statement.
Yeah, that's how I would build it. I would build it out of lots of small, tightly coordinated pieces.
Yes.
Or let's be concrete. What if you want to build a radio? What if you want to build a radio telescope with a 100,000 kilometer aperture, right?
Oh, you would
enormous.
Yeah. Well, you wouldn't have to build.
Like you would do it with lots of little pieces, right? You
Yeah.
know?
Yeah, you would.
And you'd try to be very clever about how you focus the radio waves.
Well, we're already building it with several thousand. We have them with several thousand kilometers already. It's called very long baseline interferometry.
And so if you want to scale that up by a few, several orders of magnitude, you probably would have to put it in orbit to fit it.
Oh yeah. In fact,
then,
the Russians have actually done a demonstration of that already.
Yeah, so I think that's sort of like the type of megastructure we can actually imagine building today.
Yeah.
Sure.
Yeah.
Nobody wants to front the cash, but it's not conceptually impossible.
A small megastructure is the International Space Station up there right now. It was put together modularly. Little points were joined together like a bunch of Legos, and then they fly that out there. They built that out there.
I'd push back against that.
Like, more.
Does that count as a megastructure? The International Space Station? What exactly do we count as a megastructure?
It's typically something that's unique in its size and engineering. It's not
as big as the Cowboys' new football stadium. So, I mean, it
seems to me that because of our interest in discovering alien civilizations, a megastructure in this context has got to be something big enough for us to see from Earth in one way or another, or detect from Earth one way or another.
If you're talking about an alien megastructure.
Yeah.
But there are all kinds of megastructures that already exist. So if you're talking about a high Earth orbit or something megastructure, then okay, so that's what we're talking about. It's a whole different thing. If that's what our megastructure is going to be.
Here's a question. As far as I understand, the closest we're on track to get to interstellar observation is in about 40,000 years, Voyager 1 is going to get within 1.6 light years of a star, I think it's called Gliese.
Yeah.
And
but by then its battery or its power source will have gone.
And right. And if we wanted to, we could try to give it a kick and maybe get a little bit closer. Yeah,
but we can't use it to detect
Suppose we had
anything.
been smarter back in the 70s and could have designed it so that it would have been capable of sending a signal that would have taken another couple hundred years to get back to us once it finally gets there. What is the smallest resolution object that we could have conceived of detecting when we designed that experiment?
Well, that experiment was designed for the Grand Tour to get the outer planets of our solar system. If something was specifically designed to use a gravitational slingshot trajectory to get a probe, a terrestrially manufactured artifact going at the highest rate possible and to the closest star we could aim it at with a gravitational trajectory, it would be a very different situation. But people like to say, well, the Voyager is on track in 40,000 years and it's going to pass as close to a star. But that's just an artifact of the mission that is left over, and it's going to still be coasting in space maybe 40,000 years from now if it hasn't been destroyed by accident before then. But if a mission were specifically designed to use a gravitational trajectory to get to a relatively nearby star, we wouldn't be waiting 40,000 years, and we could give it a bigger, harder boost to something closer by.
Right. So we'd probably be waiting 1,000 years with current technology.
With current technology, yes.
But see, the problem with that is that within 1,000 years, our technology would have advanced so much that the original mission would be totally obsolete.
Yeah, and as a science
Maybe
fiction,
or maybe not.
as a
Depends
science
how
fiction,
binding the laws of physics are as we understand them today.
as
Well,
a
you could
science
build a
fiction author-
telescope that would do better job of observing than your probe, and you have to figure out how to power that probe for 1,000 years, which is not easy.
There are a lot of science fiction stories that involve later technology catching up to old technology. So that's a well-known path.
It's a pretty easy trope to to dig into.
Including colony missions, of course, that can be, there's some interesting tragic stories of people in a generation ship finally arriving at their star's destination to discover that in the meantime they've discovered light speed transport from Earth, and the whole new civilization is sitting there waiting for these poor people who've been traveling through the void for forever.
But I think the question still stands in terms of defining a lower bound for what counts as a megastructure. What's the smallest civilizational construct you can conceive of that would be detectable using technology that we can currently conceptualize?
Well, it's got to be a small as the smallest thing we've discovered with Kepler so far, the smallest planet we've discovered with Kepler so far, or perhaps a touch smaller. That's the current limit.
Something
of our
more or less
observation.
Venus size.
Well,
But how would you distinguish a natural from an artificial
Well, we
satellite?
can't.
Well, we don't know what artificial would look like.
Yes, we do. Tabby star.
Well, I mean, we didn't know that.
A beacon might not be a megastructure, but it would be certainly detectable with current technology.
Yes.
You're saying if it was shouting out to us?
Yeah, if it was targeted or even if it's non-targeted, if it's large enough, it would be detected by us.
A Bedford beacon, which is intended to sort of advertise the presence of a civilization over.
Or any large steady signal.
Well, maybe it wouldn't be a civilization at all. Maybe it would be some type of unknown dying body out there that was just throwing off in its death throes this little signal we've never seen before. And we would just, extrapolate it was a civilization. We might see that more than we realize.
Well, we don't see it.
I think this relates interestingly to Daniela's question from the pre-show thread about why we conceptualize megastructures in terms of energy usage or energy signatures as opposed to other metrics. It sounds like it would be perfectly reasonable to conceptualize them in terms of detection signatures, which might have more to do with some sort of integral over power output over space and time, and I'm not quite sure how to make it precise. Like, a Benford beacon versus a star mining solar beaming facility, those have very different energy signatures, but they're quite different in terms of how we currently imagine engineering such devices.
Well, a Bedford beacon, we know how to engineer them now. We just don't know how to make them big enough. But we could build a prototype of one now.
Could you imagine making a Benford beacon that is likely to be detected by a civilization of our level in X amount of time before they would detect our energy signature, simply from how we're harvesting
I can imagine
energy of our own
that.
star?
Like our old TV programs.
With enough money, you could build a big enough beacon.
Well, I mean, we get more sophisticated about this every year, but it's a question of money. And in fact, that's what Benford's considered was economics. They assumed that energy would be costly, no matter what kind of evolutionary path you had arrived at the mastery of microwaves. You would still have to pay for energy.
That's the binding constraint, is that you have this inverse square law that's saying you can only get X amount of power out to X distance. And so it ultimately boils down to energy. This is basically I'm trying to understand the extent to which one should really think about this in terms of Kardashev type civilizations that are defined in terms of their energy usage.
Well, I don't think it's quite
that
Kardashev civilization. I mean, we don't really know that this sort of infinite expansion notion is at all likely. It's by analogy to biology. You know, you leave living thing in a medium where it can grow, and it will keep growing, right, until it reaches the bounds of its medium. The reality is that an entity that can think for itself may choose not to keep expanding.
Well, it's interesting in this context when we start talking about like this, that in Dyson's original 1960 paper, which was the search for artificial stellar sources of infrared, he specifically couches it as this is not about understanding the intentions or psychologies of aliens or other civilizations, but it's about trying to find a detection signature that is not based on anybody intentionally transmitting to us. So he came up with this, a civilization of large enough scope of energy usage is going to produce infrared radiation, and we would be able to find that infrared radiation regardless of whether they are signaling to us or not. So we can make a distinction between intentional things like beacons, or even you could say semi-intentional things like our signals that we've allowed to propagate into space, not specifically to signal, but they're out there. And the unintentional, if you build something really big, it's going to have heat waste, and that heat waste can be detected if you have the right technology.
Right.
And how valid is that distinction? Like, here we are 50 years later. Here we are, we're thinking about METI, we're thinking about beacons. Maybe it doesn't seem totally obvious that the distinction between passive energy signatures and signatures under the presence of what you might imagine, at least plausibly, are quote-unquote inevitable signatures of a civilization that seeks to expand awareness of itself might be,
like engineered signals that have a booster every once in a while, just that would keep them going forever and ever and ever.
Well, actually, it'd be a lot easier to just put more power into them than
losing energy. You wouldn't have to lose energy.
We come up with some set of vectors where we think are most likely to be, you can imagine our civilization comes up with a set of direction which we think civilizations are more or less likely to exist based on whatever criteria we come up with, and we put successively more powerful boost beacons in those directions and try to push out those ways.
I have trouble figuring out why any sane civilization would want to advertise itself.
Oh,
would you? There
are sane civilizations?
Well, there only has to be one.
It's just hubris.
Well, it depends on how common you think civilizations are in the universe. If they're as common as they are in Star Wars or Star Trek, they would be all over. If they're extremely rare, and there might be one somewhere else in the Virgo supercluster, but nowhere else, then it's so far outside our light cone, it becomes a moot point unless it's a Kardashev's type 3 civilization that's broadcasting as brightly as a quasar. So even if it were at the edge of the universe, we could still detect it.
Well, yeah, and we know there's not. We know from the work of a couple of different groups that there's no obvious such signal out there, at least with close to Earth, close to our own galaxy.
To the extent you buy the hypotheses behind those.
Well, yeah, there's a lot of assumptions that goes into it, but
there would only have to be one. If you had a civilization that was broadcasting at the energy levels of a K3 civilization, it would be as bright as a quasar, and you could see it across the known universe if you were in its light cone. Obviously, if it's outside your light cone, you're not going to see it.
Well, but I mean, just the waste heat from a K3 civilization. If you assume that it consumes the lion's share of energy in the galaxy, we don't see that.
That's right. I agree. We don't see that.
The GHAT study, and there was another study looking at how galaxies' brightness varies with respect to their rotation rate, which is a well-known thing called the Fisher-Tully relation, which if a galaxy was off that line, it would be anomalous. Both those studies concluded that Kardashev 3 civilizations, if they exist at all, are very rare.
If I remember correctly, they found that there was no detectable signature above the expected baseline, right? I mean,
that's right. Well, the sensitivity of that study requires that these K3 civilizations are consuming a huge chunk of their galaxy's energy. They have to be consumed. I believe the number that GHAT used was 85%, which is a lot.
So in particular, for civilizations within the Milky Way, it sets only a very loose upper bound on what type of civilizations we're talking about.
Well, that's K3 civilizations are quite different qualitatively from K2 civilizations.
Fair enough. Yes.
K2 could be common. We don't know. We just don't have enough information. We know they're not. We know they're not.
Safely say that they're not common either in our galaxy or in our local cluster, because once again, they would be pretty visible.
Well, okay, they're not. Given the sensitivity of the IR surveys we have today, they're not common right in our local neighborhood.
So is there anything that we can say scientifically about kind of K1 plus civilizations within the Milky Way?
Probably not.
One thing I want to pop in here is that what our understanding of detectability, what we can do and what we perceive as capable for detection for a higher civilization might just be child's play. So you can't base everything on what we could possibly detect from another civilization. Other civilizations probably have much better, much more sensitive detection capabilities.
But we're not talking about what they can detect. We're talking about what we can detect.
Well, yes, but if you're talking about a civilization looking for us and we're sending out little signals saying, hey, here we are, come play in our neighborhood, well, it could very well be that they picked us up a long time ago because their detection capabilities have already sussed us out.
This is really a question of
we don't know.
how much, civilizations that generate vast amounts of waste heat, which we don't. We don't generate that much compared to a K2 civilization. We have a limited capability to find that. We can find it. There are all kinds of stars that have an IR excess, but there are problems with all those measurements. So possibly the answer is the null hypothesis that there are no K2 civilizations nearby is correct.
I think we owe Daniela De Paula some discussion about the underlying assumption behind this discussion, which is
she should have been here.
Fair enough.
It's 3 o'clock in the morning where she lives.
Well, we should
raise this very interesting question about why is it that we think that quote unquote advanced civilizations will have these enormous heat signatures and massive energy usages, and is that just like some kind of cosmic phallic symbology that we're imputing upon cosmic history?
I agree. I think we use our own civilization as a measure because all we have.
Yeah, we can't get away from it.
We assume that we're going to want to continually grow and increase our population and consume more and more energy. But you might have a civilization which gets so much more efficient at using energy, and a civilization that doesn't believe that you should keep on increasing your population. I mean, even on Earth here, we're starting to control our population growth.
Or there is some form of energy that we don't know about yet, a form of energy that is abundant in the universe. What if dark matter was something that another civilization can harvest right this very moment? that's almost, you'll never run out of it.
Fair
don't
enough.
know.
Yeah, and I'm
we
sympathetic to those ideas, but I'm also worried. Maybe worried is the wrong word. I'm open to the idea that there's in fact a deeper kind of thermodynamic sense, like a basic physical principles sense in which we should measure civilizational advancement in terms of energy usage, and that's kind of the right metric on some deeper level. I don't know. I'm curious to know, Nick in particular, I suspect has thought about this a little bit.
Hit it, Nick.
and I would suggest that's true. We can multiply what ifs all day long, but ultimately we have to go with the science that we have at the present time, and we have to extrapolate from that, however mistaken it may be. We can select an arbitrary point in our time and say, well, what if we extrapolated the science of the 16th century? What would that bring us to? Enormous sailing ships like Kepler imagined going between the stars, but that's not going to happen. But there might be ships going between the stars. They just won't, go like Kepler thought. In any case, we know that there's certain things we know from contemporary science, and we know that the basic organic molecules are very common in the universe. We can look with spectroscopes into other galaxies and see that these basic building blocks that would be used in a macromolecule are widely available, that water is widely available in the universe. So we know that the constituents of life as we know it are available. We know that the energy flows from stars on planetary surfaces are going to be the most likely place that emergent complexity is going to arise, because you've got energy flows meeting with mineralogical complexity of a planetary surface. And if we extrapolate from that life as we know it arises, then civilization as we know it arises. And if civilizations arise commonly enough, that there might be millions of civilizations exemplifying all kinds of alternative paths we didn't take, but there would only have to be one out there that had grown very large, that was interested in being seen or communicating with other civilizations, that had chose to either try to find out about us or try to contact us or any other civilization. There would only have to be one among all those ifs. And I think with what we can see from extrapolating life as we know it, intelligence as we know it, technology and civilization as we know it, that there's no reason to think that this isn't possible, and there would only have to be one out there doing it, and we don't find even one.
But it might even be deeper than that, right? I mean, there might be an anthropic principle at work, a kind of teleological sense in which you expect there to be one, because if there is one, you're on some deep level, you're more likely to be in a universe in which there is one than in a universe in which there isn't one.
Well, didn't
maybe that's not
Jason
well justified.
Jason Wright, he argued that he thought there should be at least one galactic super civilization per galaxy. So they are out there. Now, if they're out there, they probably know we're here. They are out there. We can't detect them.
How confident are you on that?
That's a huge assumption. You cannot
but
say
that is not
they are
my
out there.
assumption, gentlemen. That's not my assumption. That's this astrophysicist's assumption.
But Jason,
I don't care. This leap from life is likely to be out there, and civilization is likely to be out there, is a vast assumption.
I can't imagine it's a leap. How there could be a leap?
It's a huge leap, and no one has yet convinced me that it isn't a leap like that. Life may be common, but we've got no idea whatsoever about the frequency of civilizations. And Nick says there may be millions out there. Well, maybe there are, but there may be none.
Well, I know, but Drake started that. Drake started that presupposition, and they've been working at that ever since.
I'm not saying
that
there. I'm not saying that there are. In fact, I'm a skeptic. I think we're alone in the universe, to put it bluntly.
I do too. Well, certainly in the galaxy, anyway. I do.
Wow.
Well, I mean, what we do know
but it's
from
easy to prove me wrong. It's easy to prove me wrong. All you have to do is
Yeah, that's right.
find
You just-
an alien civilization.
One unambiguous signal, and that's the value of SETI, is its ability to falsify with a single unambiguous, and that's the worth of SETI, in my opinion.
Yeah.
Even if it's
We should
unlikely,
definitely look. We should
it
definitely
can
look.
easily falsify with a single unambiguous signal.
Yeah, I'm totally in agreement.
there are problems with finding an unambiguous signal because
Yes.
no, there's probably the vast majority of galaxy, nearly all of it, doesn't know we're here, and wouldn't be trying to transmit in our direction except by pure chance.
I disagree with that.
Why would we even think they're transmitting on a wavelength that's even close to the order of magnitude of the wavelengths that we detect?
We can
Backward
detect just about
compatibility.
any wavelength there is. I mean, that's
The backward compatibility of civilizations. We know the stages we
There
went
are
through.
many, many wavelengths, right? If you, it depends what your prior is for the distribution of wavelengths.
Well, isn't that why astronomers have identified the so-called cosmic watering hole, where there's a signal that's likely
well,
to
you
be
try
easily
to figure out if somebody were the reasoning is if someone were trying to communicate with a civilization they knew nothing about, right, or one that had just appeared on their receivers, they would probably try to find the least common denominator. What would everyone know about, right? Well, everyone would know about the 21 centimeter line in hydrogen. If you
Possibly,
I know,
but maybe they would say,
no,
we'll
if you've
whatever
mastered
chemical signatures most,
if you've mastered microwaves,
like they might just put out power in wavelengths that are like in powers of 2. Put out scales.
well, there's
Whatever their typical energy level is.
you could sit down all day and
particularly-
come up with all these speculations, but
Well, Cripes, comets, you could say a comet was a civilization then if it's throwing out a certain megahertz, but no, not everybody
not.
in the universe is
But-
going to know a certain hertz rate, and that signal.
they would, Marcia, because that is when you point a radio telescope, which is, if you've mastered microwaves, you're going to be able to do this. You point a radio telescope out to the universe, you see that signal all over the place. Why? Gigantic clouds of monatomic hydrogen are all over the universe. And they
If
put out
they've mastered microwaves.
Well,
What
if they
don't give
haven't-
a hoot about microwaves.
if they haven't, then why?
The basic question is, what do you have a prior about what wavelengths on which a completely unknown civilization is likely to be sensitive to?
Yeah,
Yes, I do, because
really.
when you to learn how to deal with the it's not a question of what their basic sensory organs
That's just you
can
talking as a
see.
human, Paul.
No,
You
no.
have no.
No.
Yeah.
No.
You know what aliens
I
think?
understand your point about there being certain key levels that are meaningful because of basic physical properties of the universe.
Basic physical properties
I'll
of
grant you that,
materials.
but like
That
if
we know about.
But the sensitivity spectrum, like the range in which they're likely to be looking, what's your reason for having a prior about that?
Well, it's the technology for developing sensitivity to longer wavelength electromagnetic fields is an awful lot easier to develop than technology that's sensitive to short wavelength magnetic fields.
Is that a fair assumption?
I think it is.
Saying because kind of the energy required to focus to concentrate the power of the signal.
No, just to be able to control and receive that signal and detect it. Concentrating microwaves is a lot easier than concentrating gamma rays, and detecting for anybody, because it's basic physics. It's not a question of, we humans, we detect electromagnetics in the order of like 400 or 500 nanometers, which is much shorter wavelength than radio. Our eyes detect it.
Detectability and sensitivity. That's what it all matters.
But
detectability
it's
and
not that hard to
sensitivity.
take a piece of wire and have it pick up a piece of metal and have it pick up electromagnetic waves. And we saw in our own case development from being able to pick up frequencies on the order of kilohertz to frequencies on the order of gigahertz in less than 100 years.
Yeah, and it's really, 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 really primitive.
But
No, it's
kind of
not.
an
It's
interesting
not
question,
primitive.
right?
We're really good at it now. That's the thing.
We're good at it, but like it's an interesting question, right? Like we started with some technological baseline, and that technological baseline has something to do with the ubiquity of certain elements in the universe, right? Which we think are subject.
Well, it's not just the
You know,
ubiquity
like-
of elements, the ubiquity of energy. I mean, we know that there's a lot of energy in certain wavelengths that's easy to detect.
But also ubiquity of metals that are capable of transmitting signals at certain wavelengths.
Well,
With certain degrees of
conductors. If you don't
efficiency.
have electrical conductors, you're never going to master electronics or electricity at all. And in fact,
Right. So there are some kind of cosmic statistical guiding principles that suggest favored wavelengths in which one should look for information that would be transmissible on grand cosmological
well,
timescales.
if you're looking for something that everybody should know about, right? Not just something that maybe you're particularly biased towards, you would look for a common line in the electromagnetic spectrum. And now it's not going to be in the visible range because that's too easily confused with other things. You would put it in the radio spectrum because you know that even people with crude technology for detecting electromagnetic waves should be able to detect radio spectrum. And we've been able to do that for about 70 years now.
More than that, surely.
Well, in terms of, the hydrogen, the H1 line, which is about 1,420 megahertz, we've been able to do that for roughly since World War II.
Okay.
That World War II spurred an enormous amount of development in receivers and transmitters and so on.
We need more World Wars.
Yeah, that's why we needed some more World Wars to. Well, we kind of run out of we're kind of out of World Wars now, so we have to find some other reason to.
for the next 6 months or so.
Yeah.
Well, we need to move it up into space and have a big space war to accelerate our spacefaring technology.
Well, Robert Wright made the argument in his book Non-Zero that for all their horrors and suffering, war has spurred tremendous amount of development over the millennia. You may not like that idea, but it does seem to be real.
Well, I still think we're terribly hampered by coming from our own point of view all the time. It's like something wherever you go, there you are. We cannot get away from thinking as we think, which is so limited. And, it's laughable that we would even try to think what you do, you
think
like.
You think what you think, and then you do an experiment. And if the answer is no, you're wrong, then you think differently. But you
can only know you're wrong if you know what's right.
No, you don't have to know what's right. You just have to know that you got nothing.
Or you got a
no result
falsified.
Yeah.
Well,
I guess the practical signal would be something like you look out in the universe and you look for signals that are interesting and you see nothing statistically significantly distinguishable from the baseline, right?
Well, you have to develop.
That's the common pattern.
You have to develop sophisticated models of what you're seeing, right? I mean, you can't just say, oh, it's a bunch of noise, because there's all kinds of interesting things out there. It's not just white noise. There are massive spikes in the spectrum in various places. But you have to look at it and say, well, what's my understanding? So you have to develop a model. It's actually a very sophisticated set of models, and these have gotten better and better over the years. So, the work that's been done has been quite remarkable. We should be proud of it, actually.
Sure.
We
For
know
humans to understand their universe.
we know a lot about where most of the radio spectrum comes from, and the stuff we don't know, we're narrowing it down pretty fast.
But okay, so we've been pushing out from some kind of human baseline spectrum center point. And
Right.
how generalizable is that experience that we've had as a civilization? Like,
I think that Paul's point is that if another civilization is trying to communicate or trying to send a beacon, which is going to get the most exposure, or if it's looking for other civilizations who may want to communicate, then the hydrogen line or the water hole part of the spectrum is a good place to look. And I think that is physically true for any civilization. The issue to me is that unless you're deliberately wanting to broadcast yourself, the kind of communications that we now have today, only with the electromagnetic spectrum, have happened within a very, very short period of time, as Paul says, over less than 100 years. In another 100 years, we may not use those technologies at all to communicate. And so if we want to communicate with another more highly advanced civilization, we may use a completely different method that we haven't thought of yet.
What
so
we would
there may
know
be a
about,
small
what we
window
would know
of time.
about we would know about the earlier
know about the
technological
physics.
stage we had passed through, and we would know that
That's right.
civilizations probably master radio frequency communication before something more exotic than that.
yeah,
Sure, but what I'm trying to say, I suppose, is that there's a short window of time in a civilization's development in which those kind of radio communications are going to be emitted
Meaningful.
or more meaningful for them. And so, the odds of us catching another civilization at that very moment in their history is very unlikely.
But all civilizations would have this backward compatibility, and we know that radio frequencies can be propagated over galactic distances because we can detect, radio loud galaxies from very, very great distances. And if civilizations pass through a stage of electrical technology, they'll know that they can do this, and they'll know it's possible. They can continue listening at a very low cost. And if your civilization is big enough, you could transmit at a very low cost. It's not like it would have to be a huge investment. Although, as you pointed out earlier, the Benfords have focused on the economics of it and focused on cost-saving beacons. That if you have automated manufacturing and materials and energy, you don't have to go to that.
well, there'll still be a cost factor. There's no reason to believe that no matter how advanced the civilization is, that they're not going to have, costs and profits and investments, and those seem to be more or less. We don't know how universal that is, but it's a reasonable assumption that any other civilization would have some kind of way of allocating resources. And,
Well, maybe that's why some civilizations build megastructures and send them out as a bunch of little moving, self-propagating beacons everywhere, which brings us back to the whole reason we're having this podcast on megastructures. Megastructures are civilization's way of saying, we are here. You can follow this signal.
well, you could build a transiting megastructure. If something, you could build a megastructure, right? You could build a transiting megastructure that advertises your existence
And
pretty
Coca-Cola.
straightforwardly. Why?
That's the same way Stephen Hawking feels, David. Don't let him know we're here.
Why would you? Well, no.
Seriously, why would you want people to know?
Well, why would you build a pyramid in Egypt, right?
It's not the same thing. It's not the same thing at all. I mean, it's more like you're out in the wilderness with possibly hostile tribes around, and you light a big bonfire to let everybody know that you're there. Is that what you would do? It doesn't seem very rational to me.
Well,
how was that not like the Egyptians?
Well, everybody knows that Egypt was there. There was no hordes over the horizon who didn't know that Egypt existed.
The hordes
Of
came
course
over the
there was.
horizon, though.
And eventually, in the late Bronze Age, the Sea Peoples pretty much destroyed every civilization, and Egypt only barely survived. So maybe that was bad for Egypt to be so obvious.
And they were so ostentatious. You might want to say, hey, we're poor folk, pass us by. But no, they spent millions of person hours building these huge monuments.
But that's what Danielle was saying, that humans are captive to their culture. They want to throw out calling cards. Look how great we are. We built this thing.
We do.
There's a
And
need.
people aren't necessarily scared of invaders. They're not scared of death.
Well, some are and some aren't.
Yeah.
It's a bell curve.
There's up, if you ever get to the Orkney Islands in just north of Scotland, actually it's in Scotland, there's a stone ring that was built there about 5,000 years ago by a very small population that lived on the island. It was the island doesn't support a large population. It's mostly fishing, a little farming, and it's but there's this big ring there called the Ring of Brodgar. It's quite large considering the size of the people of the population. The stones are enormous, and they were probably much larger than they are now. And they built tombs nearby. So they apparently thought this ring was some kind of portal into the next world. But it must have consumed virtually all their resources beyond survival to build such a thing. And they not only erected the stones, they built in a nearly perfect circle. They built this very deep trench around them in a circle. There's a long, long history of doing things of expending proportionally vast resources for these things that don't have any obvious value other than...
But Paul, that was their beacon set in space and traveled through time.
Well, we now know 5,000 years later those people,
existed because of that.
Well, I mean, we've dug up their villages too, but
right. Well, but they were targeting us the same way that we're imagining targeting transgalactic species, right? I mean,
I don't think they did it for us. I think they did it for themselves.
That's not so clear, right?
Well, they put all these tombs around it. Apparently, the local chieftain.
The motivation is not clear, and we can go back twice as far in history to one of the most interesting archaeological finds of recent years, which is Göbekli Tepe, which was a mound in Turkey that predates. It's a pre-pottery Neolithic site. It predates organized agriculture, but it has huge monolithic architecture, and there are several other hills that probably have similar things in the same area. And it's about 11,000 years old, give or take.
Yeah, I've been to the
that's a very
Valley
good example.
of Gourmet.
They were clearly not targeting anything that we conceptualize as civilization in the modern day, right? They didn't have many concepts at all at that time. Right. They had some idea, some very vague idea about what the future was, about civilization.
I don't think they thought in terms. It's a commonplace among historians that pre-modern people usually think in terms of cyclical history, which is Mircea Eliade, this great historian of religion, wrote a book about the cyclical history, and you find survivals of this all over in every culture in the world has the idea that there's really no advance. There's just a big cosmic cycle. And one of the things that distinguishes Western civilization and the tradition that has come out of it of industrialized civilization is this unidirectional linear history with a past, a present, and a future.
Progress.
And progress, yes, progress that goes along that line. And the people who built Göbekli Tepe almost certainly had a cyclical conception of history. I doubt they thought of the future anything like in the terms that we think of the future. And they probably had a very different conception of the world than we did. But nevertheless, they created something of such permanence that more than 10,000 years later, it's still here for us.
Most of those ancient civilizations really had a reverse idea of progress. The idea was that there had been a golden age in the past from which everything has deteriorated. I mean, even the whole Garden of Eden thing. But
Absolutely.
certainly the Greeks and the Romans had this concept of a lost golden age, which mankind have fallen from.
Yeah, that's another
kind of
consistent. That's another consistent feature that one finds all the. I call that declensionism, the history of decline, which is another very common feature. But that's it. If you have a truly cyclical conception of history, it embraces periods of progress and periods of decline. So it goes around. So there's a decline, there's a fall, there's a rise and a fall, and a rise and a fall, and so on, and nothing ever really changes in essence. But whereas in a linear conception of history, things really do change. And so, if we had the Big Bang and then matter comes into existence and then stars and galaxies and then life, and there really is a progression from simplicity to complexity over time.
Until it all contracts and goes away and starts another cycle.
Until the heat death of the universe. So then, we can assimilate this Big Bang perspective of big history. We can assimilate that to cyclical history if we suppose that the whole thing deteriorates into entropy, into nothing, and then it reassembles itself into something else.
Wow, man.
So where does that leave us with megastructures? Do alien civilizations build megastructures for the greater glory of God? Is that what we're suggesting might possibly happen somewhere around some other star?
Well, we can multiply the possibilities as to why, if there are many civilizations, I'm sure they have all kinds of different motivations for doing so, if they do so.
If I'm going with my gut, I feel like there's an entropy reason why they build them. I think they build them.
Well,
They build them to continue, for continuance.
Yeah, exactly. They're doing what the most obvious form of emergent complexity in the world is life, and life does two things: it survives and it tries to reproduce. And if you survive and you reproduce, you grow, and if you grow big enough, you exceed your planet of origin and you become something that's detectable from interstellar or even intergalactic distances.
Which is where we are now. That's where we are now.
We're on the cusp.
We are starting to leave our planet in our lifetime.
We don't use anywhere near the energy the planet has impinging on it.
We're very wise in that way.
Well, no, we're not.
I'd like to think we are, Paul.
Why is it an exaggeration?
We're not using the current star's output anywhere near as much as we're digging up ancient energy and polluting the atmosphere.
But we have many sources of energy. I mean, there's other probably aliens in far-flung galaxies that cannot take advantage of thermal heat, geothermal heat. There's probably aliens in other parts of the universe that have no conception of what geothermal heat would be. But it works pretty good for many parts of our country. And it's just continuously renewable. So we aren't using it up.
One thing we do know that are common in the universe is stars. And
yes,
stars put out starlight. And starlight is a source of free energy.
But you have to know how to harvest it correctly, or it just is very passive. For most everything, it's very passive.
Well, I mean, life figured that out billions of years ago with photosynthesis. So
here on this planet,
just by random chance, we came up with a way of harvesting it. So
a way of harvesting it.
There's actually some people think photosynthesis may have evolved twice. So it seems like it's a pretty necessary condition of having a planet with starlight falling on a regular basis.
Well, you think that sheer evolutionary pressure would indicate that any bug or whatever that learns how to harvest that free energy would have a great advantage over
Oh
ones
yeah,
that could. Sure.
yeah. And you
Well,
know,
I don't know. The particular photosynthetic pathway seems relatively, I don't know what the word is, contingent to me. Like the photosynthetic pathway that we use on Earth is very, very contingent. It's adenosine triphosphate, and the particular molecular pathways that we use for harvesting energy from the sun is very specific.
yeah.
It's
But
far from.
that's all
far from
biochemistry.
universal.
You just described biochemistry. It's
I mean,
all,
there's certain, I guess you could imagine that, like, from a certain level of abstraction, there's like certain absorption spectrums, certain energy absorption spectra lead to certain absorption, energy absorption, energy emission spectra, and you can imagine photosynthesis mediates from one to the other, but like it's far from determinate.
well,
It's not obvious that we end up with.
you might have a different chemical mechanism for capturing photons that are longer wavelength than
Yeah, you would.
the green
could
ones that we
imagine
can. But we don't really. I mean,
millions difference of very many, a huge variety of pathways for that.
sure.
There may be alternative forms of emergent complexity that are driven by insulation from stellar sources. Yeah, sure. It'll be fun to discover those when we eventually get to other planets.
Yeah, like I don't want to overfit to the fact that we have a particular ecosystem which we've observed particular types of harvesting of solar energy. Like, I mean, on some level, all our energy comes from the sun.
On every level, all energy, all beingness comes from the sun.
Well, we know
everything is contingent upon that.
Well, we know that there are also there's simple life forms that live off the thermal vents coming from the ocean floor, and they don't use photosynthesis. They use a chemical synthesis based on the heat and the nutrients that are available from the superheated water jets coming out, and there are also nutrient-rich water jets coming out from the ocean floor. So
But
we already know.
if we didn't
We
have
don't
a
really
sun,
know
it
that,
wouldn't
right?
matter.
That's the hypothesis.
No, we do know
they're-
that. We do know that.
No,
yeah.
these microbes do exist, and
I mean, we know that such microbes exist, but we don't know what the probabilistic circumstances were.
No,
for the
none of it would
development of such
exist. None of it would
microbes.
exist if we didn't have a sun, you guys. It would be a moot point.
No, the ocean vents could still spawn life even without a sun.
Would we have an ocean without the sun? We don't know.
There are a lot of subsurface.
What places do we know don't have suns? Every
Well,
place has a sun.
but we know a lot of places have subsurface oceans where the sun is negligible.
Yeah.
Absolutely, and don't forget that there are wandering planets which have been thrown out from their solar systems, so that if you had a planet that was tossed out into the interstellar space, far from a star, but still had it was still contracting and getting gravitational energy, using gravitational energy as it contracted, emitting energy as it contracted, then it may well still have thermal vents. It may have an iced over ocean like Europa and so on. So it's conceivable that life may evolve between the stars.
Do any of you have strong opinions about the likelihood? Sorry, I'm not going to formulate this very well. There's a challenge to the idea that other planetary bodies, particularly moons of Saturn, etc., that have liquid water, etc., and various other prerequisites of life, may or may not be particularly suited to life because the energy gradient relative to the energy gradient that we have on Earth. I guess Europa is particularly notable in this regard. Like, I've heard it argued that because the energy gradients that one can observe on Europa are small, relative to the ones that we have on Earth, we shouldn't be particularly optimistic about the chances for life evolving in such contexts, because for basic thermodynamic reasons.
Well, we don't. There could be pretty strong gradients in places.
There's enormous amount of energy. It's just not coming from solar insolation out there. It's because these moons of the gas giant planets like Jupiter and Saturn are subject to gravitational tidal forces, and that's what's made Io the most volcanic place in the whole solar system. Is its core is getting flexed by the enormous gravity of Jupiter. And
sure, maybe there's some exceptional circumstances, but
well, no, that's not exceptional.
That's a small probability kind of.
Well, actually, all these moons of the gas giants, they're being flexed by this huge gravitational force, and that's why they have subsurface oceans. They're iced over on the surface because it's damn cold out there, but where their cores are being mushed back and forth by the gravity of Jupiter or Saturn, they're warm at their centers because of that gravity.
I mean, this is actually a deeper question about the Drake equation, like in terms of how important are energy gradients to the kind of lower level stages of the pathway towards the emergence of life, intelligence, etc. I mean,
well, if there's no gradient, there's no free energy to harvest. So you have to have.
There's no flow of energy without a gradient. So yeah, gradient is important.
Gradient is definitely important, but how unique is the circumstance of the Earth in this regard? You know, it's in the habitable zone, it has various other geological and thermodynamically unique circumstances. How special is it, really?
I doubt it's all that special. I mean, we've already got a catalog of planets, smallish rocky planets in the habitable zones of their star. They're all exposed to similar levels of stellar insolation on their surfaces.
And is stellar insolation the right metric in terms of which to evaluate the uniqueness?
Well, it drives energy flows on the surfaces of planets. Planetary surfaces have material resources. Stars give out energy resources. These energy resources drive energy flows on the surfaces of planets or planetoids or comets or anything else.
But there are other determinants besides insolation, right?
Sure.
I mean, insolation is not the unique determinant of energy gradients, right?
It's not the only. It's not. It has its unique features, but as in the case with subsurface vents or volcanism that could be driven by gravitational tidal forces, it's not the only potential source of energy gradients. And we can certainly imagine other more exotic forms of energy gradients. I wrote an answer on quarterly civilization. If we imagine a planet in the far future when planets are much more enriched with heavier materials, you could have a planet with a whole lot of fissile materials that keeps itself warm by natural nuclear reactors like the Oklo reactor in Gabon.
That would be pretty cool, but
that would be pretty bizarre.
Well, it's not how realistic it is, right? I mean,
it's not realistic now, but in the later stages of the Stelliferous era, when there's a lot more heavy elements, there may be a lot of planets that are just one big nuclear reactor, and they'd be very hot.
I think it's a very interesting question.
Well, we see volcanism on Mars, we see volcanism here on Earth, we see volcanism on Venus. So volcanism happens. It's a question of whether you have enough liquid around that volcanism to exploit it as a.
I think the context in which I heard this question raised was about specifically what one should think about the prospects for the Europa mission program that NASA has going forwards. There's a lot of kind of hype about maybe there's some moons that have some liquid water, blah, blah, blah.
But this is megastructure talk night, isn't it?
We've drifted off into Europa.
We are so far afield. And I have to tell you that talking about all this energy, my iPhone is nearly depleted because Apple decided it didn't want to have a charger and a headphone device. It combined them. So I'm dying, and my star is turning very dim, and I am leaving you now.
That's what you get for being an early adopter.
Yeah, well, at any rate,
These kids.
Go back to megastructures. That's what people came here for. Megastructures, megastructures. Think megastructures.
It's a valid point. Valid point.
Bye.
Anyway, but we're just about out of time. I think we've been
we're analyzing the energy foundations of megastructures.
Yeah. And one of the reasons for building megastructures was about collecting as much energy as you can from your star. So it's relevant, I think, about do civilizations really need to keep consuming more and more energy all the time?
Well, whether or not they do, in fact, whether or not they have to, they do, in fact. And our civilization on Earth has proceeded from, well, let's go back before civilization. Human beings started by exploiting their environment more effectively through hunting and gathering, that we were able to go into every climate and make a living for ourselves. And then we started agriculture, which is a more intensive deriving of energy from primary producers. And then with industrialization, we were able to tap into more energy sources, and we can imagine even further energy sources beyond those we've tapped now. So we've certainly seen a gradient of increasing control of energy resources as civilizations become more complex.
That's true, but perhaps it's a temporary period in our civilization, and that the more and more efficient we become at using our existing energy sources, or more and more efficient in what we do as a civilization, you can imagine a civilization which uses far less energy than we currently do now.
I completely agree.
I strongly disagree. Think
about things like think about Marsha's iPhone for a second. 20 or 30 years ago, to have a system, a computer system which was able to crank through as many operations per second as Marsha's iPhone or my iPhone, would have involved a huge, vast room, probably with lots of very energy inefficient vacuum tubes and God knows what. It would have chewed up a vast amount of power. And now we have something which is operated by a battery on a trickle of power. So, to have this, get the same effect. So it's certainly possible that as we develop more, we can become far more efficient at our consumption of energy.
But also, I want to emphasize the sociological aspect, which I think was one of the messages of Daniela de Paulus's comments on the pre-show discussion thread, which is, at one time, we thought civilization was headed toward everything bigger and better, and what I earlier called Stalinist gigantism, reversing rivers in their courses and building factories as big as cities and things like that, and ever-expanding populations. And right now, at the beginning of the 21st century, that's not the direction of civilization at all. And we can easily imagine a more advanced civilization that has systematically, whatever their energy use is, they systematically reduce their footprint. They might even make themselves completely invisible in the universe, not because they don't want to be seen, but just because they want to have a light footprint on the universe, and enjoy the wilderness that is the universe, a cosmic wilderness the universe is.
That seems to me like it could be a temporary accident. I mean, there's a reason to decrease one's energy consumption, but how to say?
Well, doesn't that entail? I mean, sort of assuming everybody's monolithic and doing the same thing for the same reason, but if there's some element in your society that wants to grow, they're going to grow, and they're going to eventually swamp everybody else, right? Mm-hmm. So it
sort of depends. If if your population outbreeds other populations, then you're going to displace, and you're going to be genetically represented in the later populations. But if that growing population has a lower technology level and it displaces the higher technology level which is what's happening now, the industrialized countries, have phenomenally low, less than replacement birth rates, and all population of the growth in the world today is from the poorest parts of the world. If industrialized civilization is replaced by if essentially pre-industrialized civilization, then the whole of industrialization merely becomes a temporary, ephemeral process that disappears.
Well, I wasn't really thinking about biological population, more just the owning the lion's share of energy, free energy in the environment. It may not have anything to do with biology at all, actually.
But human beings are not constrained completely by biology. I mean, we do far many things that aren't driven by purely biological imperatives. So I
But
think
they're surely influenced by it. I mean,
oh yeah, I mean we're not totally free of it, but nevertheless, the concept that you have to keep growing, that you can't control your population. I think
growth isn't necessarily more population.
All right, growth of energy use then, whatever metric you like to choose. Increasing growth is not necessarily
to push back
essential.
against Paul. Like, I mean, on a sufficiently broad scale, isn't it all about population growth? I mean,
well, you could have a rump population of a formerly large, intelligent species that all they do is superintend a huge mechanical or AI network that does everything and continues to grow in terms of energy usage and building things. There just aren't that many biological entities left supervising it.
That's a good point.
The biological entities may eventually become pets.
That's one of the scenarios. That's the soft landing singularity when our machine masters keep us around as pets. In the hard landing singularity scenario, they just wipe us out, not necessarily because they hate us, just because we're annoying and irritating and they can do it.
Well, we are, apparently. We're pretty good at being annoying.
Why we would annoy machines who don't need water or air, and they could just as well live in space. I'm not sure.
Probably because they read our tweets, but
well, let's not go there.
Anyway, we've about an hour and a half into this, so as much as I'd like to keep going, I think we'll defer that to another day. Marcia's left us, but I would like to get recommendations from each of you. Could be anything. Could be a website, a book, anything you like. So let's start with David. I think he already has one queued up.
I do. It's always a book with me, or nearly always a book. And the book I've been reading recently is called Black Hole Blues and Other Songs from Outer Space. The author is Yana Levin, who's a scientist who's been involved with the search for gravitational waves. It's quite an interesting book in that it was written before the first detection of gravitational waves by the LIGO instruments, but it's really all about the long development of the study of trying to find an instrument or to build an instrument that would be able to detect gravitational waves from things like collapsing stars or colliding black holes and so on. And there's an epilogue at the end where she then brings it up to date with the actual detection. But it's very interesting. There's a lot of human interest in terms of the way that science is actually done and the conflicting personalities and the struggle to get funding and so on. So it's definitely a book I would recommend. And I will also recommend my own blog, which is where I do a lot of book reviews, and it's called Megatheriums for Breakfast. There's a reason why, Megatheriums for Breakfast. And it's at the website megatheriums.com, which is hosted on Medium. So there you go.
Okay, Nick?
May I preface my recommendation with a short comment on megastructures?
Sure.
I would like to suggest that in the earliest part of our discussion, we talked about the building monuments, and people who discuss early civilization sometimes define civilization in terms of monumental architecture. But it occurred to me in the course of our discussion that each civilization builds the monumental architecture or structures it is capable of building. And we could turn that around and say we could define a civilization by the mega structures it can create. So in the earliest parts of civilization, the mega structures were the things that we've talked about, the temples or the structures at Göbekli Tepe, or the Orkney Islands monument you mentioned, or the stone megaliths, basically. And then the mega projects were possible we could do was like the building railroads around the world and a highway system. Now the mega structures we could build would be an International Space Station. And in a future iteration of civilization, the megastructures could be the kind of things we talked about that we usually associate with very old, large civilizations like Dyson swarms and the like. So with that, I just wanted to record that thought. And my recommendation is atypically, I want to recommend the work of a young heavy metal band called The Raven Age. They opened for Iron Maiden on their Book of Souls world tour of Steve Harris, who's the bass player for Iron Maiden. So they've just released an EP of 4 songs, and I think they are quite good.
Okay, The Raven Age. I'll have a link in the show notes. Okay, Sam.
All right, can you hear me?
Yes.
My recommendation is it's called, sorry. Trying to find the website. Excuse me.
Oh, I see it right here.
Yeah. It's Anatoly Karlin, the A Short History of the Third Millennium. And it's a discussion of the third millennium through the lens of, I guess you could describe it as futurism, maybe I'm not sure what the right term is exactly. But hard to describe. But I recommend this essay. Let's put it that way.
Okay.
I'll leave it at that.
That's good enough. My recommendation, very brief. The Mozart, the 6 Haydn quartets and 6 string quartets, and a box set by the Budapest String Quartet. Music almost straight from heaven, even if you don't believe in heaven. Okay. So that's it for episode 65 of the Unseen Podcast. Marcia Barnhart has left us, but I'd like to thank David Grigg.
Thanks. Good to be here.
And Nick Nielsen.
You're welcome. Thanks
And
for having me on.
Sam Lichtenstein.
Sure.
And we would love to hear from you, as always. Just go to unseenpodcast.com, and there's links there to everything you need to know to get in touch with us. You can email us at unseenpodcast@gmail.com. And if you'd like to be on the panel, that's easy. If you don't know how to do that, just email unseenpodcast@gmail.com and we'll let you know how. The next invitation will go out for episode 68, which will be in late February. So if you think you'd like to be on a panel, you don't have to be an expert in anything. You just need to have good questions, and we'll get you on the panel. And you can participate. This is an open participation podcast. What you've heard tonight has not been edited and has not been scripted in any way, as you probably already guessed. So, good night. The music is by DJ Spooky, and we are distributed under the Creative Commons Attribution Share Alike license. Good night.